Am I audible? Everybody is able to hear me, right? Yeah. Uh, are there any PhD scholars out here in the room? You are Professor Avnish's student? Your name is Ruchi? Jayashri. Any more PhD scholars in the room? Yet to come. Uh, any master's students? Any master's students? The rest all are undergrads. So one Avnish's PhD scholar is there, right? Ruchi. Yeah, yeah. Okay. Yeah, we'll wait. I'm just uh, trying to set the stage. So those who are, what is your area of PhD? Okay, good. No, first year PhD is great help. For today's assignment. So today's topic is a little interesting in a way. Next year we are looking at a ACM school for 2 weeks on just today's topic. So there is going to be a challenge to cover this in 3 hours. So we are going to be a little, experimental doing this today. Our hands-on will involve a little different way of doing things today. So goal today, in my view, my personal view will be to understand challenges of AI loads in compilation. We cannot understand the AI compilation, or we cannot uh, write small pieces for a ML compiler or ML kind of workloads in a 3-hour session. We brainstormed over the what we want to do in hands-on, and we could have been done some piece which we could have wrote with the help of GPT or something in 3 hours also. But what we chose is to make everyone aware of challenges of ML compilation so that you can solve the problem later on. Solve is a big word. In ML compilers, we are only mitigating because we don't understand a lot of things yet, and the loads are evolving every day. So what I will say is, if we are able to mitigate some of things in, maybe 1 year after this class or 2 years after this class, that will be great achievement. So two PhDs, right? Any more master students in this room? 2 PhDs we have. Yeah. So no, these 2 PhDs also I'll make them TAs along with you guys for the session. Okay, good. So we are definitely gonna short on time for today's session. Not for the information part of it, which I will be giving you, but solving or trying to grasp challenges of ML compilation. So how I am planning today is, till now you folks have covered compilers, the traditional our compilers, which are required for even ML compilation and everything. But you have not been introduced to the variable load, and one of the variable load is machine learning. So in, I'll say 40-45 minutes, I will try to cover challenges of handling, machine learning or AI kind of loads in compilers. Another 40-45 minutes, We will look at MLIR, which is another high level IR below the LLVM IR, above the LLVM IR, which is trying to help us solve machine learning load kind of problems. One of the paths. There are many paths people are taking in the ML compilation. So MLIR is one of the paths people are using. And then there is an interesting assignment. There are two parts of assignment. One for today. We will make group of how many we do have? 5, 5, 4, 9, 9, 3, 12, 12, 3, 15, 15 and 3, 18. Yeah. So we'll make group of, maybe 2 folks or 3 folks and 3 challenges we are going to talk about: shape, loops and sparsity. You can pick any one of them, you can pick 2, you can pick 3. You brainstorm in the group in that time after presentation, and your goal is to, towards the end, every team is given couple of minutes. So there are 2 parts to that assignment. I'll explain that once again towards the once I finish the lecture. What you have learnt till today in this ACM school or in your undergrad course, postgrad course, use those techniques to mitigate one of or more than one of these 3 problems, what you could have been done with the what you know already. Let's say you know about constant folding, loop unrolling, memory allocation based on the variable type and all those stuff. So whatever you know till date, you brainstorm, and 1 minute your thoughts on that, like how you will mitigate these one or many of these 3 challenges in ML compilation load. Part 2 of the assignment, the next 1 minute, use your internet, use ChatGPT, use whatever you want to use, and figure out what other techniques are already available to take care of shape, loops and sparsity. So total 2-minute presentation per team, and to mitigate these problems, so that will be our exercise. We have 2 TAs who know more than me, Rahul and Mitesh. So they will be helping each group where you are stuck. I will be helping the group where we are stuck. Then we will also have our 2 students of this group, which are PhD candidates. I consider them, as good as the TAs. Help them, the groups, or be part of the groups in that assignment. Now the interesting part of assignment comes next, which is the optional one. After the session, you have till February end, you have time. So go back. So read 3 to 10 papers where compilers is mandatory, maybe for AI or on DSP, or compilers for AI on DSP. Figure out 3 to 10 papers, summarize them from this is an optional assignment. Summarize them, like what those papers were, why they took those independent variables, could they have been done differently, could there have been different results, could there have been different dependent variables. So critique these papers in max 3 pages, Optional assignment, the optional part of the next 1 page after 3 pages is 1 page if you want to build a literature review out of those papers. Last optional page is if you want to find out a problem statement out of those papers. With this optional assignment, I will leave my email ID. You can send it to me. We'll have the TA's email ID because they will be definitely interested in this exercise. The good part of this assignment is if your literature review, if your analysis of those papers is good, if you are a third year student, you will have shot at Qualcomm's internship interview. And if you are a final year and eligible for campus placements, then you have a full-time employment opportunity interview at Qualcomm. So this is the second part. It's a purely optional assignment. It's up to you folks to do. I think we shall get started, right? Any questions before we start? Okay. Again, as I said, the goal is to introduce challenges for compilers with machine learning load. So let's get started. So this is the agenda. So ML models are getting bigger and bigger and much more complex. There are different kind of challenges which are there. Another thing which is happening with ML compilers is traditionally the most of the code came from C, C++ kind of languages, and we as a compiler engineers were very good at handling C, C++ or those kind of loads. But now the ML compiler, most of the languages are pretty high level. Then what happens is challenges with the shapes. What do I mean by shape here? In traditional compilation techniques, you utilize knowledge of the variable type, which inherently is the variable size also. Let's say if you say FP16, int 8, or any variable, you know how much memory size it's going to take, how many registers it's going to consume. So it's easier for the compiler to handle. Here shapes are nothing but tensor shapes, which are kind of equivalent to your variable size. So for example, if you look at images, it can be 224 cross 224 cross 3 channels, 224 cross 224. You can look at, so this is static size, right? Static size. But static size will not be there when you are handling images. The sizes is gonna change. So you are not going to know what is the size of image coming in, or the voice. If you are processing the voice, it can be 1 second long, it can be 10 seconds long, it can be 1 minute long, it can be multiple minutes long. So the shapes you can consider here as equivalent to variable the tensor shapes. So you will not know what kind of tensor or what size of tensor shapes are coming in when you are going to compile them. So shape challenges, you don't know how much memory to allocate. If you want to tile, or you want to segment that image, or you want to do a fusion of multiple images, you don't know what sizes are coming in, because if you tile an image, let's say you know the image size, you tile them in four equal sizes and then process them. But if you don't know what is the size of the image, what will be the 4 equal sizes? If you do in runtime, it's expensive. Compilation we do in advance. That's why we are able to do things faster. Loop optimizations. Now, loops are based on what? When you write simple loops, let's say I is less than X, or I is less than J, I is less than whatever number, whatever other variable. So here, there you will know the loop size, because you will know the variable type, you will know the value allocated to variable, what you are gonna anticipate. Here, The loops will be based on the shapes because shapes are your variables. Like if you are tiling an unknown image size, your loop sizes are gonna be unknown. How you are gonna unroll, what kind of loop optimizations you are going to use. So that is another challenge. Sparsity is in, let's say, in neural networks, there are a lot of tensors which will be zero. Now, doing the operation, if you are gonna operate on every zero tensor, you are just wasting your MIPS from your or processing from your processor, you are wasting battery, you are wasting time. So you are taking the performance and power both penalty. So those zeros can be ignored and can be used in our favor. The zero tensor can be used for to make compilation faster. So these are the three challenges we'll be looking at. This is the agenda of just the first part. Second part, I will introduce MLIR quickly and then we'll move on. Is that clear till now here? So as I said, these are static shapes. Very compiler friendly, compiler will love it. Tensor dimensions are known at compile time. A compiler can pre-allocate the memory, optimize the layout. If I have to tile this, in whatever the equivalent sizes, very easily known. I can process this, I can allocate memory, and like this is the image classification 224 by 224 image size with the RGB, 3 RGB inputs. Now, if tensor dimensions are vary across input or runtime, if we don't know what is the size of the image, compiler must reason symbolically or defer decisions. We can take some penalties, we can have shape assumptions, we can do multiple things like you have run the code for enough time and you figure out that this is the most anticipated shape size we are getting. And we compile assuming that, and if there are errors or if there is something is wrong, runtime we change it, we take penalties sometime. One example can be LLMs with variable length sequences. There can be many more examples. So I'm trying to keep the explanation as simple as possible for this part. Any questions here? We are clear the challenge here, right? We don't know the shape of the tensor. Tiling everyone is aware of, right? Tiling everyone is aware of in the image. Why we do it, how do we do it. If there is even a single person has a doubt of what tiling is, I can quickly tell that in 10 seconds. Okay. Why statics shapes are easier to compile? Compilers love predictability, right? They work best when they know exactly what to expect, which static shapes, everything is predictable. Memory needs is how many times to repeat the operation loops, how data is stored, memory layout you can do in advance, fixed loop bounds, so you can do tiling and all these kind of vectorization and all those things you can plan for in advance. No runtime checks because it's static. Your decision like whether you want to unroll a loop, you want to tile or you want to do the fusion, you can do it confidently. Memory reuse and layout planning are very deterministic. For example, a CNN trained on, as I said, 224 cross 224 images can be compiled and reused. When you know that every image is going to be 224 cross 224. Embedded model with fixed input sizes benefit from the tight memory control. So in these cases, static shapes, but in reality, there are no static shapes. Most of the cases, there are no static shapes. Yes, there are cases where we bound the shapes. Let's say you are building uh, let's talk about a design where you're building an IoT device, which is very tight on memory, which is very tight on power consumption. You are not going to go with, then in that case, in their training, what you are inferencing running on that IoT device, you are most likely going to keep fixed inputs, because it is not only the compilers can solve the problem, even designing you might have to put constraints sometimes to uh, to solve the problem. So it's not that there are no use cases with the static shapes. You can build a design constraint when the shapes are gonna be static. You can build such systems, but practically most of the compiler loads for machine learning gonna have dynamic shapes. I should. So computing goals, because I love those computing goals. So earlier when the research used to happen on when we are trying to solve the computing goals, the most important parameter was performance. We never used to consider power much into the game, because power was not still, our systems were not so power hungry that power was still available enough for us to handle. But now with these LLMs, cloud and everything, we have become so power hungry that computing companies are talking about buying nuclear reactors, or they have already bought nuclear reactors. So now we have some additional goals in computing. This is overall, I'm not just for today's session, doing more for two things. Per milliwatt, what do I mean by this is, let's say I am able to get some performance in, let's say 10 milliwatts, and if I have to get a 5% incremental performance, but I have to spend 20 more milliwatts on it, which is more than double of our original power budget. I will look at the use case and I will design the trade-off, whether I will leave that 5% on the table performance or I will still go for that optimization. Doing more per kilobyte. Like if I have to get a 3% more performance, my memory size, my RAM size, or my, the memory size has to go 5 times higher. Will I do it? Depends. Still, there are use cases where performance is paramount, and whatever power it consumes, like training scenario, will still go ahead and spend that kind of power. So this scenario of doing more per milliwatt, doing more per kb is becoming more and more common. Earlier it was only common for embedded devices. Now I hear from my friends on the cloud side and all those other sides also that some of the companies, they say their CEOs are, first slide they want to review for their cloud project is, what is the power budget, how much power we are consuming. So in the last slide itself I specified these things, but I will again repeat. Why dynamic shapes are hard to compile? Loop bounds and memory sizes are unknown until the runtime when we say the shape. Layout planning becomes conservative and less efficient, because you will probably look at different kind of probable shapes. Then you will design it with that maybe some buffer, so that most of the things are done by the static compilation time, and when your shape comes in which doesn't fit in that particular size, you go and handle it at runtime. Fusion and vectorization depends on the shape compatibility. Let's say you have a 128 vector size, or you have 256 vector size, or fusion wise the memory, if you do the fusion, or even tiling, because tiling, let's say there is an irregular boundary and something is remaining, How do you handle that? The edges. Trade-off in code generation. General purpose code handles all shapes but runs slower. Let's say you designed your compiler such a way that it can handle all kind of shapes, but it will run slower. Specialized code is fast, but increases compile time complexity, which we have to look at because we want to do fast for two reasons. One reason is the power, doing more per milliwatt. The second one here, what trade-off will come in is to achieve this, what is the memory trade-off we are taking in. Examples, LLM input length varies from 5 to 512 tokens. Vision batch contains 224 cross 224 and 640 cross 480 sizes. Speech audio clips ranging from 1 second to 10 seconds durations. So these are very practical scenarios, and these are the most often happening scenarios where the shapes are, or your tensor shapes are not known and they are of different sizes. We are clear till here why shapes are challenging? These are again just examples. The goal of this presentation is not to solve the compiler load problems. The goal of this presentation is to understand challenges. Again, whatever I wrote as an examples, that is depicted here pictorially. Variable length sequences, text, images, you can have different sizes. Audio, you can have different length of clips. Okay. What does compilers traditionally do? These you have seen in last 10 days. Allocate memory at compile time, generate loop with the known bounds, apply layout specific optimizations like tiling and fusion. This works well for the static models. Okay. Many ML operations like processing every pixel in an image use loops. If size is fixed, compiler knows exactly how many times to repeat each operation. So we can generate the loop with the static bounds. And we can apply the loop specific optimizations like tiling. We know in what block we have to, what sizes we have to break the loop. Combine fusion operations to reduce the steps and improve speed. We can unroll the loop. This works well. Static models, no runtime, shape checks needed, predictable performance and memory uses. Example, matrix multiplication with fixed dimensions, unrolled loops. CNN with fixed input size, compiled once and reused. So, static world, pretty good. So what I think I should have written the slide differently. Because if I say must do means I know the answer, right? But nobody knows the answer. So what compilers may do for dynamic shapes should have been my things, my slide title. But I mentioned must do, that's okay. I'm sorry for that. Compilers must adapt to the shape variability. Now the shape variability adoption, there can be different techniques. Track shape information across operations. As data moves through different layers of operations in the model, the compiler must keep track of how shape changes at each step. Sometimes the exact shape isn't known until runtime. The compiler uses symbolic reasoning, like the variables instead of numbers, to predict what the output shape will be like. Here again, it's prediction. It may or may not match. Insert runtime guards to ensure shape compatibility. The compiler adds check in the code to make sure the operations are only performed when the shapes are compatible. This prevents error like trying to add two tensors of the different sizes. Of course, our goal has to be, the code generation must be flexible. We should be able to handle any size of the shape. Avoid memory access and layout mismatches. These goals, look, to write these goals, I could write very easily. But to achieve these goals, there are enough challenges. Like very simple, I've written. Reshape must preserve the element count. But there will be scenarios where, the element count is going to change in reshaping. You will have trade-offs. Split requires divisible dimension size. You may get a, image size which will not be equally divisible in the 4 if you are trying to buy tile by 4 or whatever number. So what do we do with the remainder, and how do we handle those scenarios? So these are, and yeah, so, and we need to keep track of shapes, do the safety checks, generate flexible code, and make sure everything works smoothly and efficiently. Now this is, I somehow, making these statements, I what I'll say, laughing at myself, like putting these goals so simply. Because this is the biggest challenge right now. The handwritten kernels, especially for AI accelerator with very specific architectures, not the CPUs or the GPUs, especially for inferencing, we have enough challenges out there. Like the auto code generated from the PyTorch framework, Python code, and using the Triton and all those framework for DSP like architecture, we may be looking at gap of 10+ % right now, auto generated code from high level language as compared to handwritten kernel, and 10% plus is huge. That is not acceptable. But the other side, the challenge will come to your foray is, if code has to be written handwritten in assembly or in the ISA of a specific hardware, that's not scalable. You are not going to write same MLOps across a Qualcomm DSP, a Seva DSP, a CPU, x86 CPU, ARM CPU, the GPUs. Are you going to write the same MLOps across? No. That's a challenge, almost an impossible challenge. So what can be, the trade-off? Let's say this we are able to achieve maybe through MLIR or through some other framework. That answer also we don't know at this point in time. While MLIR looks the most probable candidate, okay, 5 to 3% we are leaving performance on the table, or 2% we are leaving on the table from the auto-generated code. That makes sense. Like, we can live with that trade-off, because the handwritten assembly probably to optimize you will take 3 to 4 months, but writing the code in the Python and the compiler auto-generating optimized version of it, maybe 6 weeks versus 3 days. So productivity is also important. I think. Okay. So what are few techniques which we can look at solving handle dynamic shapes? Shape inference, the compiler tries to figure out the shape of the output data based on the shape of the input data. Why it is important? This helps compiler plan memory usage and ensure that operations are valid. Constraint solving, the compiler enforces mathematical rules like making sure reshaping a tensor doesn't change the total number of elements. It prevents errors and ensures operations like splitting or reshaping data are done correctly. Symbolic propagation, the compiler tracks relationship between dimensions, such as dimension A must always equal dimension B. This allows compiler to reason about shapes even when they are not in fixed numbers. The compiler generates code in runtime adaptation, generates code that can adapt to the new shapes as they appear during the program execution. This flexibility is crucial in handling the real world data changes. Specialized code for common shape patterns, the compiler can create optimized code for shapes that occur frequently, making the program run faster for those cases. Just-in-time compilation, the compiler generates code on the fly. So this allows program to handle shapes they have never seen before. Caching the implied code, that's a compiled code for reuse. Once a code is code for particular shape is generated is saved so that it can reuse for the same shape appears again. And this will avoid repeating the compilation process. Now, while I spoke about all these methods, everything has its pros and cons. It is not as straightforward as it is. For example, use JIT compilation to handle new shapes, there will be a delay because when you see the shape, you handle it. Uh, Specialized code for common shape patterns. Your compiled code, you have a repository for a lot of common shape patterns. Your image size may go bigger. Uh, you can look at cache the compiled code for reuse. Then again, the cache usage and all those things come into the picture. So these are commonly used techniques, or rather, I'll say we are trying to improve ML compilation load based on these techniques. We are trying to improve these techniques. We are trying to mix and match and use these techniques to get better results. But these are the directions which we can take. JIT compilation, you guys are aware of? Yeah. So this stands for just-in-time compilation. Instead of compiling all possible code ahead of the time, the compiler waits until the program is running and generates code for the specific data shapes it encounters. This is especially useful when the shapes of data like length of sentence size of an image are not known until runtime. And why JIT compilation is needed in machine learning or the AI kind of load? Dynamic shapes are common in the real world ML workloads. JIT compilation allows the program to adapt to new shapes as they appear, generating optimized code on the fly. And again, here also we can use JIT along with the caching of the known shape already compiled, and that can program can reuse the code instead of compiling it again. So caching will little bit improve the overhead of JIT compilation and speed up the repeated operations, but again it will not be as comparable as to things compiled ahead of the time. And even with the caching, there will be load when the first time a new shape arrives. It will have the JIT overload, but once that has arrived, you can cache it and use when the same shape arrives the next time. So JIT compilation along with caching gets better than traditional JIT compilation, but again, that's also not a perfect solution. Any questions till now? I have repeated the same thing again and again and again because it's the goal is to just get used to the challenges of ML compilation. Solving compiler for AI workloads is going to be very, very interesting field. It's already very interesting field. So we are okay till here, right? You understand this challenge. I don't expect anyone to have a mitigation technique or how to solve this challenge. Just understanding the challenge till this point we are clear, right? Very good. Now loop and shape are very much gonna be related because loops are generally based on, if you talk about traditional compilation, on the variable size. Here they're gonna be, dependent on the shape. Shape is unknown, so loop size is unknown, and loop size is unknown, so all the loop optimizations goes for toss, because for example, unrolling, based on the loop size you decide. Tiling, based on the loop size you decide. Uh, Fusion, based on the loop size you decide. Vectorization, based on the loop size you decide. Here the size of the loop itself is gone for a toss. So very similar to shape challenges, but again we'll look into it. I know it will be repetitive, but these challenges, I don't mind to be repetitive if people from this class go ahead and end up improving, uh, you know, these challenges, end up improving the performances. The one good part of being in the compiler world is whether you look at MLIR or whether you look at LLVM, whether you look at GCC, if you have an idea, you can implement, you can upstream, the whole world can use it. It is not proprietary solution, and the pleasure of upstreaming and seeing your code being used by the world is such a fantastic feeling. Why I say this? Because, you know, I started my career as a modem engineer, which is very proprietary technology at the layer 1. And I used to be very enthusiastic about what I do, people use it. This is early, around 2004 to 2006, when those 3G phones started getting sold in India, for which I was writing the code, because prior to that I wrote the code, but they were not sold in India. So once they come to the stores, I'll go and ask, is the call drop reduced? Now this guy doesn't know, but I worked on call drop, so I want to know that is the call drop reduced. Is the data performance better? Is the pop noise at the cell handover is okay? So, but in this case, in the open source, you don't need to ask. You can see people using your code. If there are any bugs reported by anyone, that's even more interesting, right? People are using your piece of the code. So, compiler world, in one sense, it's very good. Is what you do is being used by, if you upstream it, is being used by so many people. Of course, loops dominate ML computation. Which is the most used mathematical operation in neural networks? Matrix multiplication. What is matrix multiplication? Nothing but loop. Okay. So loops are the most used ML computation. That's why you look at, whether you look at Qualcomm neural processing unit or you take other neural processing units, the first mathematical operation they moved to hardware was matrix multiplication. So, oh, it's written here, matrix multiplication. Okay. So most operations expressed as nested loops. Performance depends on the loop efficiency. The speed and efficiency of ML programs depends heavily on how well these loops are implemented and optimized. Loop drives your memory access, reuse and parallelism. Loops determine how data is read and written to the memory. Good loop design allows the better memory reuse. For example, tiling. The biggest help from tiling we get is cache localization or better cache utilization. You guys are aware of that, or you want to see that visually? We are aware of that. Good. So optimizing loop is key to the runtime performance. Better cache usage, better memory usage. You can use vectorization to speed up. You can use threads, multiple threads, multiple parallel threads to get things faster, get better performance, and get better performance with reasonable power. Now, traditional part, you learned this on last 10 days. What we traditionally do with the loops? Loop unrolling, fusion, tiling, interchange, vectorization. Decision based on the loop size. What is the loop size? What are the nesting levels? And the target architecture. So target architecture is around 10 years back. Compiler team were compiler teams in different companies were maybe shrinking or stagnant because there were limited architecture x86, ARM, DSP was there, but use cases were only limited to computer vision, so not much tensor processing unit, neural processing units were not there. Uh, Not too many accelerators with the with proprietary ISAs or new ISAs. But with explosion of machine learning, slowing down of Moore's law, where software needs to do more, we had architecture explosions. Now, let's say you are a computer vision researcher or a ML researcher, and I ask you to write optimized code for every architecture after understanding that architecture and ISA, that's not possible. So compilers were to rescue that. Okay, people still keep writing, not even in C, C++, they go even much higher. Python, though Python is an interpreted language, but we compile it and generate the binary in advance and not interpret it for specific architecture. People use high level language, but the compiler team does the magic for compiling it optimized for the underlying hardware. And that caused explosion of compiler teams in every team, every company. Rather than stagnant, uh, as far as what I know, as compared to the number in 2012, in India at least, I know everybody has grown more than 4x of their compiler team size in all the companies who are working compilers in India. So target architecture becomes important. Target architecture caused the explosion of the compiler teams all across, because we cannot expect everyone to understand the architecture and write the code according to the architecture. These heuristics work well for the regular loops, predictable bounds, memory access patterns, easy to optimize cache and parallelism. Um, For example, unroll small loops to reduce control overhead, the loop to improve cache locality in matrix operations. Very interestingly, the compiler optimizations like PGO will go for toss. Profile guided optimization, what it does, it looks at how many times each instruction is run, how many times each function has been called. Now with the variable loop sizes, you will require more heuristics to be generated. It's not that it goes for a toss, it becomes complicated. More heuristics to be generated. Well, in ML loads, it's still not bad for PGO because there is not a lot of branching. Let me not deviate to that, but okay, let's move forward. Challenges in ML loop optimization. ML loops are often irregular and data dependent. Loop bounds may depend on input shapes or runtime data. Now again, we don't know the input shapes, so loop bounds will not know. Memory access patterns are non-contiguous or strided. So that again puts a lot of compiler optimization on the task. Fusion and parallelism are shape sensitive. How will you fuse two loops if you don't know the size of the loops? This requires and the heuristics which you generate often underperform in this setting because the loop size keeps changing. Examples: attention layers with dynamic sequence lengths, convolution with padding dilation and stride variations. We are okay with, we understand this piece because this is, that was like the shape challenges was the first most important slide in this whole slideshow. Second most is this one. I have oversimplified these challenges, but that was the purpose of today's session. Probably if we have a detailed school on ML compilers later, we will dive into these in much deeper details. Yeah. Hmm. Yes, you will be able to do, but you will need to know the bounds. Uh, so you will take your analysis will take upper bound, I will say, that this is what it will maximum go. You will not unroll a loop if the loop size can be from 5 to 5000, right? You will not unroll for 5000 times. You will know the upper bound, most likely, right? The variable size, what the loop bounds can be. You are not gonna indiscriminately unroll the loop. The bound is known. What I'm saying is like the loop size can be still be variable, but your bounds are known, and bounds, the worst case scenario also not going to, you know, change your code size or the binary size drastically. Here the bounds even are problem sometimes. I will refrain from talking in detail about polyhedral compilation. Polyhedral was covered as part of this school. No. So you can take this also as an assignment. Polyhedral can be, polyhedral. A lot of people consider it as a compiler topic. It's a maths topic. So polyhedral mathematics is very, very good for loop optimizations. Again, there is a divided school. I personally of a poly school, I believe that poly is very, very helpful in loop optimizations, but there are people with very, very drastic statement on the other side saying poly has done nothing good for the loop optimization. So poly-friendly loops, you can use the polyhedral optimizations and can get very good results. So there is a high compile time cost for the poly, but poly can be one of the way to go for ML compilations, and it will require a lot of work in poly and ML compilation both the sides. But in my personal view, again, why I'm using word personal view, because these are unsolved areas and people view can vary as per their own research results. So in my view, polyhedral models to represent loopness symbolically is a good way to go and solve ML loop compiler problems. Now this is interesting. We use machine learning itself to guide the loop optimization. Using machine learning to help compilers optimize the loops in ML workloads. Instead of relying only on the hard-coded rules, compiler can use ML models to decide how to optimize the loops. These models learn from past performance data or through training. Model can learn from profiling the data or offline training. Like ML models can analyze how code runs, profiling, and use this information to predict best way to optimize the loops. This can also be trained on offline using lots of examples to recognize patterns like the previous runs and the other example. The ML compilation can use, they can predict unroll factors, tile sizes, fusion opportunities. So what we were talking till now was compilers for ML. In this slides, I am talking about ML for compilers. Like ML being used to, I have seen some work, reinforcement learning being used for compiler optimizations. I am not, even say expert will be a bad word. I am not even a beginner in ML for compilers, but I have seen some work, I have read some papers where that's an interesting area. Here, what happens is decision is the data driven, not hard coded. Instead of fixed rules, the compiler uses data and learning to make the decisions, which can lead to better performance across different scenarios. This may enable, scientific English has to be perfect. This may enable portability across CPUs, GPUs, and accelerators. May should be the right word. Enables, I'll have to edit that. Okay. Example, the people who are using this, and you can look into these details. Yes, so not, again, go for a toss will become an extreme word. So as a researcher, we will have to figure out a way where When we use ML for compilers, I will say validation will become very important for the compiler, because verification is of course a big challenging problem in the compiler world. So you will have to trade off between, you will have to validate the compiler more than what you do regularly. There will be challenges with the correctness, yes. So that will be again a research area which you can use it, yeah. No, no, verifying on the fly will be an interesting challenge. You will use these heuristics. You don't compile on the fly. You use these heuristics to do few compilations using the training method, and let's say you run the tests offline, like you tried your technique again and again and again on a standard kind of load. So these solutions will come for a particular kind of a load, a particular kind of a model. It will may not be generic initially, and then over the time you will have to evolve, but on the fly will be a tough task to do. Yes, yes, yes. So any questions till here? Yes. I'm trying to look from my experience when we did last. So not for this case. So let's look at it how it is. It was not machine learning. So how much profile data was there? For our mobile kind of scenarios, so we wanted to do PGO for mobile. This is long back when PGO was done via instrumentation, which was not possible in mobile because there will be code size bloat. So we cannot instrument the code. And instrumentation also plays around with the timeline of the execution. So what we did was we took the traces running all kind of test scenarios which we could think of in numerous times into a text file outside through a port. And now this text file, that how many times each function or each branch has run, was input to the profile guided optimization. So in that time the profiling data was not very huge. So we'll have to again see what is the profiling data size in these cases, because for machine learning model, huge data means it goes really huge, petabytes, and so I'm not sure. There can be scenario where then such kind of data can be there, but the kind of use case I have seen, the data size will be okay. Oh, we are not doing good on time because I have one more thing to do. So maybe I will little bit speed up, but feel free to interrupt me. A little bit speed up here. So sparsity, common in large models. The sparsity can be in the uh, weights. Many weights can be set to 0 during the training, or activations become 0 due to functions like ReLU. So do you want to operate and waste your cycles on zeros? No, you want to ignore and move forward. So there should be a way to detect, when you detect sparsity, you move on. And as model gets bigger, many weights parameters are set to 0 during the pruning or activations in things like ReLU. Types of sparsity known to weight sparsity, many weights in neural networks are 0 after pruning. Activation sparsity, your ReLU set many outputs to 0. Gradient sparsity used in distributed training to reduce communication overhead. So these are the example: pruned CNNs with 80 to 90% zero weights, ReLU layers with sparse outputs in deep networks. Why sparsity is useful? Improves efficiency. Since most values are 0, you can skip many calculations and make the model run faster. For example, multiplying by 0 doesn't change the result. It has to be 0. Reduces the number of operations, fewer non-zero values. Means fewer computation which speed up inference. Save memory bandwidth and storage. You don't need to store all the zeros. Enable deployments on the constrained hardware. Sparse model fit into smaller memory footprints, making them suitable for mobile phones, IoT devices, and hardware and other hardware for the limited resources. Low power consumption. You can use sparsity to not to compute those, not to store. So ultimately, help you with the lower power consumption. One of the companies, I forgot the name, they built the weighted sparsity handling into their hardware itself. So you can check it, check that one. Again, here I explained those sparsity, like the weight sparsity, activation sparsity, and the gradient sparsity. Structured and unstructured sparsity, the entire rows, blocks, or channels are 0. Very good for ignoring them. Unstructured random 0 entries scattered across tensor. These are a little tough to handle, but a good challenge to have. Why sparsity hard for compilers? Irregular computation. When most values are 0, the pattern of which values are non-zero can be random or unpredictable. This irregularity make it hard for compilers to plan how to process the data efficiently. Unpredictability in memory access patterns. In dense data, memory is accessed regular, predictable way, like reading a book page by page. With sparsity, let's say you have a book. After 23 pages, there is blank pages, there is 1 page, and then there is again after 18 pages, after 3 pages. So how do you figure out where are the pages you have to read? You flip every page, you jump a few pages, then let's say you missed one filled page, then how do you come back to it? Loop bounds and iterations. Order depend on data. In dense computation, loops have fixed bounds. But in case of sparse data, how will you optimize the loop here? Traditional optimizations break down, like vectorization. If in your vector, the most of things are 0. Tiling. If in a tile, one is a very dense tile and another one is very sparse tile, how do you handle that? Again, fusion. The same problem comes in there. So very interesting problem, like like sparse matrix multiplication needs indirect indexing, sparse convolution requires dynamic masking logic. So very interesting problem to solve here. So again, few common sparse formats and how do they help. I'll go to summary because I have to cover the next one. Yeah. Sparsity is key to efficient ML at scale. Sparsity helps reduce the amount of consumption of memory and energy needed to run ML models. Sparsity introduces irregular patterns in computation and memory access, making it harder for compiler to optimize for the code, like vectorization and tiling, fusion, which we talked about earlier. Compiler must be aware, must be able to recognize and handle sparse data efficiently. And there is research direction, sparse IERs and dialects, creating optimizations that are aware of specific sparse format like CSR and CEO can automatically tune performance. Hardware software co-design. So yeah, that can be So this is like the people who joined late. This is your key slide for today's assignment towards the end, where we are going to make group of few folks each, where you have two parts, 1 minute each to present each team towards the end. The part number one is what you have learned till date in traditional compilers. If you have to just use that, how you will try to solve these ML compiler challenges, or mitigate. Solve is a very big word. Second part, the second minute, use GPT, search and all those. What are the different techniques which you can use, and understanding of your how to mitigate these challenges. Any questions till now? This is gonna be heavy. You may feel that you haven't got much out of this session, or you may feel that you know all the challenges. Both ways it is possible, but in both ways it is untrue, because this is a very, very important open area which we need to solve or we need to mitigate. Again, I will use the solve is a very big word. Mitigate or improving performance will be our key. Questions before I bring up the next slide? So except two PhDs, we have everybody's undergrad here, right? How many people are from third year? Right now in third year. How many people are in final year? And we have second years also? Very good. So second years, have you taken the computer architecture course already, or it's still pending? For second years, very important thing, I know you would have been, because of not having the computer architecture course yet, you would have been lost till now for a lot of things. But these things, when you look at computer architecture course or the compiler course, when it comes in your part of curriculum, these things will come together. So don't worry about it. These terms will play around. Don't worry about it. Rather, it will help you. Before I get into the next MLIR, and by the way, MLIR is not machine learning IR. Its abbreviation MLIR is not machine learning IR. ML stands for something else. Let's look at a while for now. From now, let's look at, before I start on MLIR, I will show you two slides on an architecture, because I will be talking about that architecture pretty often, and since I know that there are not a lot of people from that background, so you know about CPU, very good at control, not good at parallel processing, right? Very, very good at control. GPUs, very good at parallel processing, but not good at control. So this thing evolved. DSPs were initially used for communication systems long back, before image processing came in the picture. So here there is some control and some parallel processing. Control not as good as CPU, parallel processing not as good as GPU, but having reasonable parallel processing and reasonable control it made it very good for digital signal processing when for communication systems. So in communication systems, signals were the communication signals. And you are operating on those signals, amplifying, noise correction, adding, phase changing, and all those things. Then we figured out, well, no, mathematically we knew earlier itself, but the signal processor very good for image processing also, because the pixel is a signal. What do you change? You change the RGB values and noise, you reduce the noise and all those. So they started getting used for computer vision a lot, because their power budget will be very good. Then if you look at what digital signal processor are very good at doing is multiply and accumulate, which is matrix multiplication. And where it is used very well or very regularly is, of course, machine learning. So they found these NPUs or the TPUs which you see, they found a lot of application there also. Because inherently, again, they were not designed for it, but the architecture fit in there. So we will be looking at MLIR in context of a DSP architecture today. I will try to go fast, and 10:30 leave you for the tea, and then we can start the assignment. I may overshoot by 5-6 minutes. Kindly bear with me. Why it is hard? As I said, the architecture explosion happened and the compiler engineers were considered the magicians that, that new hardware comes in. I don't care, I write in Python, I write in C, and you generate optimized code for the underlying hardware. So why it is tough for NSPs? Because most open source compilers focus on GPUs like XLA, GLOW, TVM, and I know maybe programmability of some hardware is tough, but again another thing depends for any solution is how many hands are on the deck. So right now if you look at in the open source community, almost everybody is working for GPU. So how many hands on the deck for GPU? Thousands and hundreds of thousands. But how many are from NSP? Pretty few. NSPs are complex, have multiple core processors, smaller processing unit, help with specific tasks, making them more complicated to target than regular CPUs and GPUs. Memory limitations. Now when we were building these DSPs, or anybody is building these DSPs, their goal primary is to do more per milliwatt, to do more per KB. So memories are limited and the things are challenging. It's not like unlimited megawatts are being pushed the way we are pushing to GPUs. Most of the time they are used in handheld. So there is a data overhead, there is a tightly coupled memory which is near to the chip, and there is DDR, so there is a lot of time gets wasted shifting memory from DDR to TCM. Now the diagram on the right side of yours, I introduced in the other DSP architecture slide, so it is same as that one. There is a 4-way multi-threaded VLIW architecture. What is our VLIW is slightly different than which we implement in the Qualcomm DSP, is slightly different than regular VLIW. We pack more operations than a generic VLIW. Sorry, SMD, I'm mixing. Then we have hexagon vector extensions, which you can do vector operations for quick processing of the large data sets. They include vector register and dedicated memory for fast data processing. Additionally, the tensor units are specialized for heavy AI computations, making them ideal for deep learning and neural networks. As demand for general purpose computing and AI power is growing fast, data centers struggling with the power and coding. Running AI on the edge devices like phones, sensors, and IoT devices needs good power and performance. So that makes the DSP an ideal use case. Today's agenda is not that, but for like the other slide which I showed you, there are CV scenarios which we have done, like image detailing, low light enhancement. Performance is close to 3x of a quad CPU with neon extension, and power is 1/10 of what they are consuming in that particular scenario. So what is MLIR? So why there was need of this MLIR? MLIR is multi-level intermediate representation. So while your LLVM IR or any compiler IR is at much lower level and doesn't know what kind of loads you are running, but in some scenario you need to know what kind of loads you are running. For example, in case of not multi-level ML machine learning loads, you might have a constraint that these two ops will run together, and preserving this information till LLVM IR level or the lower level IR level is impossible. So this is like that is the reason you required a multi-level IR. MLIR provides unified structure, a common platform to support many requirements for compiling for machine learning models. It can handle various tasks needed for ML, such as graph optimizations, loop optimizations, making repeated operation loop faster using techniques like fusion, tiling, again with all the constraints. So whatever the problem statements which we were talking about, so a lot of people are trying to solve this in MLIR or TVM Apache or MLGo or Glo compiler. It can convert the high level operations into hardware specific instructions, including memory management and vectorization, so lowering the transformations. Quantization is also another interesting area. I'm not sure how many of you saw the news that recently, using 2-bit quantization, in 2 quantization and high token rate, Qualcomm was able to run on a laptop a 14 billion parameter model. So a 14 billion parameter model was running on a laptop. I think they have achieved till 28. I have seen CMU running, Carnegie Mellon running a 7 billion parameter model on a phone. So it was not running on the cloud, it was running on the phone. So quantization becomes very important to save power and make sure. What MLIR is not, it's not a programming language. It is not for low level tasks. Not in programming, and not built for register selection and instruction scheduling. So it is not built for lower level tasks. We will look at the whole infrastructure here. I think picture. Okay. So MLIR supports heterogeneous AI. This means provides its ability to build compiler for NSP, CPUs, GPUs. So MLIR is not just for DSPs. The way we are trying to, Qualcomm is, we are trying to optimize it for the DSP, but it can work for everything. Rather, it is working very well for the GPUs, quite well already, as compared to what we are doing for NPUs. It leverages open source advancement by utilizing the latest compiler development supports from a open source community. MLIR also serves as ML compiler for supporting the continuous evolution of AI models. It treats dynamic shape and loop as first class features. Like MLIR being evolved, that there will be loop challenges, there will be shape challenges. So this IR treats them as very important for ML compilation. And additionally, it can lower operations to hardware instructions or hand optimized libraries. MLIR is essential for modern programming AI languages. Python compatible programming language like Triton, Mojo requires an MLIR based compiler workflow to function effectively. So MLIR in short is a very flexible and powerful tool which you can use for it's about various hardware, leverages the latest open source tech and helps AI models and hardware evolve, plus it works with modern AI and programming languages. While this is more about the text on the slide which we talked about, so as I said, as you as students, the LLVM open source or the MLIR being open source, it is such a great way to contribute to these problems. Now, the first question comes from the student community in general is, where do I start? Well, what is it called in the LLVM community? Yeah. So start from there, start fixing them. I think MLIR community is evolving, same from the LLVM community, they are following the similar principles, and start contributing. If you wait for like I will build an expertise and then contribute, I think getting your hands dirty while being on the move, it will be a good option. And I am a big fan of open source because nothing proprietary. It gives a very level playing field to anyone working on it. So go start playing around with the code on LLVM dev website. Like the last few conferences, there are very good tutorials to getting started with LLVM. So you can start from there, and LLVM and MLIR too. So this slide shows how we at Qualcomm are using MLIR to build a flexible, powerful compiler system for AI models. The workflow supports multiple ML frameworks and hardware types, making it easier for developers to deploy AI models on devices like phones, sensors, and servers. MLIR acts as the glue here that connects high-level ML code to hardware instructions, ensuring the performance and the compatibility. If you look at the MLIR lies here, LLVM is here, so your IR, LLVM IR is somewhere here, MLIR is here. MLIR has more high-level information as compared to the low-level. It doesn't understand the register scheduling or the low-level instruction scheduling, but it has some information which as I said, I required 2 ML ops running together. So that will not be there at LLVM IR level, that information. Then they need to run together. So that's an important one. And this is how we are doing it. People can do it differently. So here is the Triton where people write their program. The lineage dialect is already existing in the MLIR framework. There is a lot of work going on. So Triton dialect is for Triton language. Lineage also exists. Lineage means linear algebra, so they take linear algebra as the basic principle. This dialect. This is the piece which comes from us, hexagon dialect, because hexagon is the underlying architecture. So there has to be architecture specific work here. So that we do in hexagon dialect. Then there is this LLVM dialect, which is for LLVM. Again, a lot of pieces for this exist, and a lot of things which we have to upstream things which may be dependent on hexagon. Then LLVM hexagon already exists. You can download the toolchain right now from the open source runtime platform and hexagon NPU. So this is how our MLIR platform looks like, and this is our current state. Hexagon direct handles optimization for hexagon NPUs and multi-core, multi-thread parallelism, vectorization, mapping to tensor units, and memory optimizations. We have successfully mapped key kernels such as MACML, Flash Attention, Softmax, Layer Norm, and others using this workflow. We are right now fine-tuning for performance. so that the hand-coded assembly we are able to, if not beat the geo mean, at least come closer into the few percentage of the handwritten assembly. Initial performance looks promising, uh, but yeah, there are a lot of challenges which we have. PyTorch is a popular framework for building and training AI and machine learning models. It is widely used because it's flexible, easy to use, especially for research and prototyping. PyTorch is pretty fast. And another reason for us to adopt PyTorch is, again, I said, lot of hands on the deck. Most of the people are adopting it, so a lot of problems are getting solved. There may be technically better solution. We really don't know. But technically, even if it is a better solution, if a lot of hands are not on the deck, a lot of people are not trying to solve the problem, it will not get solved. And Triton, of course, I explained in the last slide, it's a programming language, so Triton dialect, uh, lineage already exists. Hexagon, we are doing the major work here. LLVM, a little bit of changes. And this whole block, which we showed on the last slide, fits in here. This PyTorch framework comes from already the industry. This, our tool chain already exists, LLVM for Hexagon. And here is the runtime platform, which is Hexagon NPU. And this is how our workflow looks on MLIR. Wow, this is good. I ran through these, but I wanted to run you through those challenges because that is what we want to take away today. So, any questions till now? Hmm. Hmm. Oh, okay. So, so there are, so this is our, I will say, proprietary DSP where we started building for our own use case, and there were very, it was reverse. I will say it was domain specific architecture, and our decisions were more dependent on our use case and trying the reverse use cases for this one. So with the VLIW and the SIMD combination, we were getting the best performance and the power budget. I can show you that part. Uh, on your point as why don't use RISC-V based solution, yes, there is work on building a RISC-V based DSP which is going on. I'll tell you the benefits and the pros and cons of both. The second one where it is very proprietary, the Rs one is very specifically built for our use cases and it works very fine and our power and performance budget is very good. In case, let's say we build a RISC-V based DSP, the biggest benefit will be their ISA will be RISC-V based. So all the optimization which is done for the RISC-V you will automatically get it for this one. There will be some limitation based on the RISC-V architecture, which to keep the open source or you have to build the extensions. So there will be pros and cons for both the things. In our case, if you look at the slide, our design principle for Hexagon NPU was so hardware is proprietary, but the instruction set is not. I'll just. Oh, where is it on there? Yes, there are. If you look at here, oh, sorry. So our three goals were domain-specific architecture, tight system integration. Because at that time, the open world when we designed this was not pretty much, the thing of the world, and familiar programming model using C intrinsics. So these were our primary goals, and we were doing it for computer vision and uh, signal processing for that time. We did not look at the programmability aspect at that particular point in time. What you are talking about is, let's say we had another proprietary hardware recently, and on that what we did is we kept the hardware proprietary, but we moved the instruction set using a wrapper or a decoder to the RISC-V instruction set. Now what happens is till RISC-V, all the RISC-V compiler optimizations till the IR level what they come, we get it for free. The instruction set is same. But then we have a decoder layer and assembler, we need to do some work. So same thing will be here. If we build a RISC-V based system, we will have, it will be trade-off between the two things, I'll say. Yes. Yes, at that time RISC-V was not popular, maybe at this point. Yes, no, no. What you say is, again, it's my personal view, but the open source is the way to go, even on that side. So I'm very, very excited. Like IIT Kanpur Professor Amey is starting work on RISC-V based DSP. So that will be very interesting to watch. We are already watching that work, and if there are good learnings, we are open to it. The time we designed this versus the times now, it's pretty different. Oh, our first DSP, I don't know how old it came in. Uh, I think earlier to 2004, the first DSP. And then it evolved on version to version, then we had to maintain the backward compatibility and all those things. Yes, and we kept optimizing on top of it. And it's not that we don't watch what is happening out there. So we have our view on the risk-based DSP work going on, but it may be the right time to decide that. Because yeah, today it's not the session, but there are, in this session I talk about all the why decision, why we took this decision, why we build a cache like that, why there was, for example, if you look at this one, like, so there are a lot of design decisions here. Here there is no ISP and sensor. Sensor doesn't write into a DDR and it goes. There is a circular buffer streamer which directly writes into the L2, because you write in a DDR and write into the L2, you again have the penalty. So it was lot, for our use case, we built something very, very proprietary. Yeah. Any other questions? Oh, GCC works. So I haven't worked much on GCC, but its huge learning curve is a little slower because a lot of work has been already done. One thing which GCC, why people are moving towards LLM, of course, LLM is more modular, but it doesn't, you cannot discredit GCC because the way it evolved over the time and the way it has paved the work, it is very good. The one thing why people are avoiding, one of the reasons why people are avoiding GCC is the LLVM open source license. You can keep something private. If you have a breakthrough, you can keep it private. GCC, that is not allowed. It's part of the license. So let's discuss the assignment before we break. So I would like to make heterogeneous groups. Please help second years. I will say the final years, third years, and the second years. There should be mixed group. There should be second years. 3 second years should not be forming a group. Very simple. Okay. So how many of us are there? Total number. 1, 2. You two are TS, PhD candidates for now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, you are not part of class. You are part of. Oh. No, then I will count you as TA for this group, like mentor basically. The TAs are mentors here. 3, 8, 8, 4, 12, 12, 4, 16, 16, and 7, 23, 23, 27, 27, 31. Okay. Let's build 3 each. I see 31. I think the backside there, that's the organizing team, right? They're not part of the class. Yeah, okay. So one group will have 4 people, rest all will have 3. So form a group, form the heterogeneous group, the 2 PhDs and the Pradeep from the afternoon and probably his teammate. We will help you through your discussions. First part, try to restrict, like your brainstorming, try to restrict it to what you have learned in traditional compilers, how you will use it to solve these problems, the 3 problems which we discussed at first. Okay. Uh, and the brainstorming will be the part of learning. You will help each other. We will keep moving with the groups and look at your discussion, try to help out. We also don't know the solutions. The second part of the brainstorming will be you use GPTs, Google, papers, whatever it is, and what the world is doing through the modern technique to solve these problems. Each team will get 2-minute presentation each. So 10 teams, 20 minutes. That's cool. We'll have use the break time also. So that's the assignment for today. People got the assignment? This one? The interesting assignment, which is the optional one, is compilers is the mandatory part. This you can send it to me by maybe March 15th. Pick 3 to 10 research papers. Don't go incrementally. Don't plan for 10 at the start. 10 is a huge number for 2.5 months. Compilers for AI on DSP. If all the 3 conditions are true, that's great. But even compilers for AI or compilers on DSP, 2 conditions is more than enough. 3 to 10 papers. You read them. I don't have time to introduce. There is one very beautiful tool called as Publish or Perish. I use it for searching the papers. You can use that tool because it gives the citation index and all those of the paper, and the good papers are at the top with the keywords. Max 5 A4 pages, 12 font size, Times New Roman, 1.5 spacing. Why I mentioned this? Because I have seen people Part 1, summary of papers, how many you have chosen. Especially like I will use summary of papers, critical. Critical means can they, authors, why did they choose those dependent variables and those independent variables? Could they have been done differently? What were the results? What will the future work area? So basically, what can be future work? Results, can it be done differently? So each paper you write the summary. differently. So you summarize. This one is max 3 pages, this part, with the same specification. If you want to go to the optional part, part 2, generate a literature review out of it. So I forgot, you will search for, you will get from internet 5 C's of literature review. I think cite, critique, connect, yeah, 5 C's of literature review. And part 3, which is too ambitious, again optional. Build a research proposal. Like a problem statement for a PhD. So this is optional 1 page. Optional 1 page. My mail ID is, and anyone else interested in getting these can give their mail ID. I don't want to keep anything proprietary here. qti.qualcomm.com. So this is optional. Any good work here, the third year folks will offer you internship interview, and the final year folks will offer you employment interview. Let's break for tea, and then we start the today's assignment. Okay, sure.